Hi, Apple Grace. Hi, Katie. Can you hear me?
I can.
Okay, thank you. I just needed to have that said, okay? How we doing, guys? Peachy
Doing
Keen Wonderful?
was what wonderful?
Are we doing Peachy Keen Wonderful?
Oh, always.
Yeah, absolutely. I'm up to 10 people. Sophia makes 11. We have a quorum here, guys. All right. Basically, what I'm going to do here is I'm going to take you through some of the basic empirical formula problems. Is there anybody that hasn't been exposed to this yet?
Me,
Who's me?
Monica.
Okay, Monica.
I did watch a little YouTube and I reviewed it a little.
All right, great. Absolutely fantastic. Monica, what you have to understand, when you have a balanced chemical equation, the little subscripts that are there, what that stands for is the molar ratio between the individual elements in that compound. Does that make sense to you, Monica?
The ratio, yeah, it does.
But it's not the ratio of the grams of the elements. It's the ratio of the moles of the elements, one to the other in the compound.
Okay.
So basically what we're going to do, it's going to be a 3-step process doing a empirical formula problem. First step is always going to be the hardest. That's going to be getting the grams. Getting the weights of the individual elements is always the hardest thing. Then simply all you got to do is divide each element's grams by its atomic weight. That will give you the moles. Then you're going to have a series of moles of all these elements that are in that compound. Just divide by the smallest one. You have the molar ratio. Simple enough, Monica?
Yes.
Okay, so I'm going to take you through some different percent mass and empirical formula problems. Then we're dealing with one specific type of empirical formula problem, and that is the empirical formulas from experimental data, surprisingly enough, being as this is a lab. So anybody have any questions on the last laboratory, the mole lab? I do have to apologize to you because I had forgotten that he did that strange thing with the having to fill in the dimensional analysis portions. I forgot that he had done that. So I remembered it by the time of my Thursday class. You guys, I forgot about it. But to be honest with you, I was getting 90%. Most of you guys you got 90% on that lab. So I was really proud of you. Any questions about the last lab? Okay. When we're dealing with percent composition is nothing more than you take the part, divide it by the whole, multiply it by 100. You got a mixture of copper and sulfur. The copper mass is 3.45 and the mass of the mixture is 9.42. What's the percent copper? Well, easily enough, the percent copper is going to be the part, the 3.45. And what I'm going to do then is I'm just going to divide that by the weight of the whole, the 9.42. That gives me my percent copper. We did this experiment. We did kind of this experiment a couple weeks ago when we were doing the salt and sand mixture. We got a mixture of salt and sand that weighs 20.56 grams. We weigh a magnet. The magnet weighs 35.27 grams. When we pass this magnet over the mixture, all of the iron clings to the magnet, and we find out that it weighs 42.83. What is the percent iron in the original mixture? Okay, guys, think about this. Remember, we're getting a percent analysis, so we need the part over the whole. Generically speaking, what do I want the part of, guys? What do I want the weight of to be the part?
You want the iron?
I want the weight of the iron. Can I get that, Jeff?
Yes, sir, you can.
How can I get it?
So you know the weight of the magnet when it's empty, and you know the weight of the magnet after it has the iron particles attached to it. So you could subtract the weight of the magnet with the iron from the magnet without the iron, and then from that number you could subtract that from the weight of the mixture, and then you would have the mass of just the iron, and then you could
You're
part over whole.
overthinking, Jeff, you're overthinking. When you subtracted the magnet and the iron and the weight of the magnet, didn't you get the weight of the iron?
Yeah.
Okay.
Oh, part over whole. Okay. Got it.
All right.
Got it. Yeah.
So you're absolutely right. You got the weight of the iron and magnet, and you got the weight of the magnet. Subtract the two out, you got the mass of your iron. Then all you got to do is your whole mixture weigh 20.56 grams. Divide the weight of the iron by the 20.56. You have your percent iron. Good enough, guys? Any questions
Yes.
on that problem?
No.
And really and truly, guys, I'm looking at this as kind of like tonight as being a workshop to help you go through some of these mass percentages and empirical formula problems. Are you all kind of on that right now? Those of you that don't have me in class, is
Yeah.
this where you're kind of at in
Yeah.
I think we're a little past this.
stoichiometry, Jeff?
Yeah.
Well, I just started stoichiometry tonight. So, but it's
Yeah, okay.
around the same area.
Yeah.
Has any, other than Monica, has anybody else not had this stuff yet? Okay, so guys, I'm looking at this as a workshop. So as I'm going through the problems, I'm going to be asking questions. And more importantly, I need you to ask me questions, because literally speaking, guys, that's how you're going to learn. I'm a resource, guys. You're paying me money to ask me questions. Do it. All right. I can also get mass percents using chemical formulas. Remember, we're doing the part divided by the whole. And the part is going to be each element's contribution. The whole is going to be the entire molecular weight. So if I'm looking at sodium dichromate, I look at that, I have 2 sodiums. Each sodium's atomic weight is 22.99. So sodium's contribution to the molecular weight is 45.98. Chromium, I also have 2 chromiums. Each of them has an atomic weight of 52 for a total of 104. I have 7 oxygens, each at 16. So oxygen's contribution is 112. I add all of those up to get the molecular weight of 261.98. Now, simply speaking, in order to get the mass percent of each one of the elements, all I got to do is take the element's contribution, divide it by the molecular weight. I have the percentage. So for sodium, that was 45.98 divided by the molecular weight. I got 17.55% sodium. Chromium, 104 divided by the 261.98. I got 39.70% chromium. Percent oxygen, I got 112 divided by 261. That gives me 42.75. And you know the beauty of this, guys? The absolute beauty of it. These percentages do not change. As long as I have a chemical formula of sodium 2, chromium 2, oxygen 7, those percentages are not going to change. So if I get given a weight, if I get given a weight of 363.2, then if I know that I have 363.2 of my sodium dichromate, I know that of that 363.7 or whatever the number was, 17% of that's going to be my sodium weight. 39.7% of that number is going to be my chromium, and 42.75% of that overall number is going to give me my grams of oxygen. We are going to use that fact later. All right, new problem. We have a sample of silver oxide. If you take silver oxide and you heat it up, what you do is you take all the oxygen away from the silver and you're left with pure silver. So I weighed my silver oxide at 42.87. After I heated it, the sample weighed 39.91. What is the percentage of oxygen in my silver chloride? Jennifer,
Yes.
can I get a weight of oxygen?
Yes. You can subtract the 39.91 minus or from the 42.87 to get the oxygen that was taken out.
Simple enough. That's what I do. I now have my part. I now have my weight of oxygen. Now the tricky part, Jennifer. What am I going to divide it by? Am I going to divide it by the 42.87 or am I going to divide that by the 39.31?
The 42.87 because that's both of them together.
The 42, as you said, the 42.87 is the weight of silver and oxygen. So I'm going to divide my weight of oxygen by my weight of silver oxide. I do that and I get 6.90%. Anybody confused? Is this making pretty much sense on what we're doing here, guys?
Yes.
Yes.
Yeah.
Okay. Now, if we're dealing with empirical formulas, now, first of all, you have to know the difference between an empirical formula and a molecular formula. A molecular formula has the exact number of atoms in that particular model, in that particular molecule. A molecular formula has all the atoms. An empirical formula, if we look at the subscripts within that molecule, and all the subscripts can be divided by a common denominator, then we can divide it by that common number, that common whole number, and we're left with the smallest whole number ratio of atoms within the molecule. That's the empirical formula. Molecular formula has all the atoms. Empirical formula is the smallest whole number ratio of atoms within that molecule. All right, if I'm dealing with sodium phosphate, if I have one molecule of sodium phosphate, Maverick, how many atoms of sodium do I have?
One molecule of sodium phosphate. That's 3.
How many atoms of phosphorus?
1.
And oxygen?
4.
Okay, now, Monica. Monica?
I'm here.
Okay. Now, Maverick just said if I have one molecule, I have 3 atoms of sodium, 1 atom of phosphorus, and 4 atoms of oxygen. Do you
Mhm.
buy that?
Yes.
All right. Now, what I'm going to do is instead of just having one molecule, I'm going to say I have 6.02 times 10 to the 23rd molecules of
Mhm,
sodium phosphate. Would
mhm.
you agree that I now have 3 times 6.02 e to the 23rd atoms of sodium?
You lost me at the last part.
Okay. If instead of having just one molecule of sodium phosphate, I have Avogadro's number of molecules of sodium phosphate.
Okay.
Since I have 3 atoms per molecule, wouldn't you agree that I have 3 times
Oh.
Avogadro's number of sodium atoms?
Yes. I think.
And wouldn't you say I have Avogadro's number worth of phosphorus atoms?
Yes. Yes. Sure.
And wouldn't you say I have 4 times Avogadro's number of oxygen atoms?
Oh, I see where you're going with it. Okay.
Good. Okay, so I've got this number of sodiums, that number of phosphoruses, and that number of oxygens. But this number is 1 mole's worth. So in effect, if I have 1 mole of sodium phosphate, I have 3 moles of sodium, 1 mole of phosphorus, and 4 moles of oxygen. Or my ratio is 3 sodium to 1 phosphorus to 4 oxygen. Does
Okay.
that make sense to everybody?
Are you gonna do
So in
the? Sorry.
No, all right, you started first.
Are you gonna do next where it's like if it's like not a whole number?
We'll get into that, I promise.
Okay.
So this next person was a male voice. I didn't necessarily know who it was.
Yeah, it's Philip. So in this situation, is the empirical formula the same as a molecular formula because it's the same number of moles as it is to molecule?
No, the reason, Philip, is you can't divide 3, 1, 4 by any number other than 1, can you?
Right, that
Right?
makes sense. Okay.
So if this were
Right.
something
Lowest
like,
common denominator.
if the molecular formula were Na6P2O8, I could divide each of them by 2 to get the empirical formula of Na3PO4. Does that make sense, Philip? What you're looking
Yeah, that
for.
makes sense.
If I had, just going to add a slide here. If I had a molecule Philip, can those numbers, can the subscripts be divided by a whole number? What's the largest whole number that will
divided by
go into
3.
each one of those?
Or 6.
6. So if I divide that by 6, my molecular formula for glucose is C6H12O6. My empirical formula is CH2O. Does that make sense, Philip?
Yeah, that makes sense.
So basically what I'm saying with that is the subscripts are the molar ratio between the elements in the formula. So when I'm doing an empirical formula problem, I have 4 steps. First step, I have to get the masses of all the elements in the formula. Generally speaking, guys, this is going to be the hardest part because everything else is basically just written in stone. Once I get the masses, I turn them into moles. Then I'm going to look at the moles of each one of the elements within my compound, and I'm going to find the smallest one. And I'm going to divide each of those moles by the one with the smallest amount. Now, has anybody ever seen a chemical formula with a fraction as a subscript? Ever?
No.
Oh,
You
That sounds
can't.
like an absolute nightmare.
You can't, because you can't have half an atom. You can't have a third of an atom. So when I'm doing these, my molar ratio may give me a fraction, but I got to correct it. I got to correct it by multiplying by integers until I get rid of the fraction. But I have to multiply not only the molar ratio that's the fraction, I have to multiply the other molar ratios as well. We'll get into that with a practical example that will make that a little more self-explanatory. My compound, sodium sulfide, has 32.9 grams of sodium, 23.1 grams of sulfur. What is the empirical formula? I have the grams. Step 1's done. Step 2, I got to turn it into moles. So I take my 32.9 grams of sodium, divide it by the atomic weight of sodium. I get 1.43 moles of sodium. My sulfur, 23.1, I divide it by my atomic weight of sulfur at 32.06. This gives me 0.720. Step 3, which one of those two is smaller?
0.720.
So I divide both of the moles by the 0.720, and I get 1.99, which is close enough to 2, and I get 1. So my molar ratio of sodium to sulfur is 2:1. Simplest problem I can make for you guys in empirical formulas. So if my molar ratio is 2 sodium to 1 sulfur, all I got to do is put that ratio as the subscripts. My formula is Na2S. Are we okay here? We're fairly on solid ground, guys?
Yeah.
A compound. All right. That's one way to do it, is from the masses. We're going to get masses again in a second. A compound was assayed to be 26.6% potassium, 35.4 chromium, and 38.1% oxygen. What is the empirical formula? Now, at first, this freaks you out. This freaks you out because basically you don't have any grams. You have nowhere to start from. Our first step, remember, is finding grams of each element. So pick a number, any number. And isn't 26.6% of that number going to be potassium? Pick a number, Philip, any number.
7.
Okay, I got 7 grams. So I take 7 times 0.266. Of that 7 grams, 1.86 of it is potassium. And I multiply 7 times the 0.354, 3.48 grams of that 7 grams is chromium. And I take 7 and multiply it by 0.381. That means the 2.67 grams of that 7 grams is oxygen. So guys, I now have my grams. But let's be sensible about this. If I choose 100 grams as my fictitious amount, wouldn't 26.6 grams of that be potassium? And wouldn't 35.4 grams of that be chromium? And wouldn't 38.1 grams of that be oxygen? Isn't that true?
Yes.
Yes.
If I did it for 77, these would be the amounts. So the easy way is to pick 100 grams. I'm going to choose 77 just for kicks and giggles. And 0.266 times 77 gives me 20.5 grams of potassium. 0.354 times 77 gives me 27.3 grams of chromium. 0.381 times 77.0 gives me 29.3 grams of oxygen. Next step, turn them into moles. I divide my grams by my atomic weight. I get 0.524 moles of potassium. I get 27.3 divided by 52. I get 0.525 moles of chromium. 29.3 divided by 16. I get 1.83 moles of oxygen. Hunter, what's the smallest number I have here?
20.5.
What?
Are you talking about the grams or are you talking about, sorry, it's 0.525.
Close enough, 0.524. Doesn't matter, we're close enough. So I'm going to divide
Oh,
the
sorry.
0.524 into each one. I'm going to divide it into the 0.524, I get 1. I'm going to divide it into the 0.525, I get 1. I divide 0.524 into 1.83, I get 3.9. I get a fraction. So my mole ratio I came up with is 1 to 1 to 3.5. I got to get rid of that fraction. So I'm going to multiply the 3.5 by 2. I come up with 7. That's a whole number. I can use that. But if I multiply the 3.5 by 2, I have to also multiply the chromium mole ratio by 2 and the potassium by 2.
Why are we, how are we multiplying it by 2 though? Is that just arbitrary?
No, it's not, Hunter, it's not arbitrary.
You have to get it to the closest, like the closest whole number possible.
Yeah, I know it can't be a fraction, but
So-
why
Right.
2?
Because, okay, you start at 2, Hunter. I multiplied this by 2 and came up with 7.
Yeah,
It's a whole number. All right.
Okay.
Say this number were 3.33, right?
yeah.
I multiply this by 2. I get 6.66.
It's not going to work.
Not going to work. So I'm going to multiply it by 3. This gives me 9.99. Close enough to 10. Okay?
All
Okay,
right.
Hunter? If
Okay.
this number were 3.23, I multiply this by 2. This gives me
Not going to work.
6.46. Multiply it by 3. This gives me 9.69. Doesn't work. I multiply it by 4, and this gives me
12.9.
12.92. Close enough. So what you're doing with these fractions, you're starting with 2. You're multiplying 2 by the fraction. If that gets you a whole number, you're done. If it doesn't, try 3. If
And so
3
on and so
doesn't
forth.
work, you just keep on upping the integers until, guys, if you get up to 10, God bless you. If you get up to 10, you got to figure out, hey, I must have done something wrong. Start off from the beginning again, because we're not going to give you something that crazy, okay?
There's a list in the survival guide that he has where it's like, if it ends in 0.25, you times it by this. If it ends in 0.33, you times it by this. So he has a whole list of like rules to follow if it ends in a certain number like that.
Dynamite. If you want to go ahead and memorize those, fine. I
What-
like
hey,
my
what
way
page is
better.
that?
I don't have it on me. It's module, I think 8.
No, it's this.
Okay.
No. Andrew, it's also should be in this. I'll check later on. It should be in this manual as well.
Yeah, because that's a good resource.
Will the answer need to be in its simplest form?
What do you mean by that, Michael?
Like if you can only, if you could times it by 2 and it'll work, but you could also times it by 5 and it'll work? Does it matter
The
which
smallest
you
one,
use?
Andrew.
Michael,
Okay,
but it's-
Andrew.
thank you.
Andrew, I can multiply this by 4, couldn't I?
Sure.
I can multiply this by 4, and I can multiply this by 4. And that would give me a thing of 4.
4.
So 4,
And then 13.96. Is that close enough, right?
14. All right, Michael. Do you see this, Michael?
Yeah.
All right, now, can I divide these numbers by any number?
2.
Remember, the empirical formula is the smallest whole number ratio.
Gotcha.
So yes, 4 to 4 to 14 works, but that's not going to give you the empirical formula. The empirical formula is the smallest ratio, which is 2 to 2 to 7.
There we go. Understood. Thank you.
Okay.
Okay? All right. This and the next problem are going to be kind of like what we're dealing with in our lab today. I got 98.3 grams of manganese. I put this in a container that has 100% nitrogen and heated it up. The resulting product had a mass of 140.0 grams. All right. Now we have to determine the empirical formula. Remember, our first step, determine the weight of each of the elements. In this particular example, I have manganese and I have nitrogen. Do I know how much manganese, if all the manganese reacted, do I know how much manganese I have?
Yes.
How much?
Don't you have 98.3 grams of it?
If all of the manganese reacted, yes, I have 98.3% or 98.3 grams is going to be the weight of my manganese in my product. Now, how much does the nitrogen weigh?
You subtract 140, or 140 minus 98.3 to get how much nitrogen weighs, how many grams of nitrogen there are.
Do you all see that? If my compound, the only thing I can make is a combination of manganese and nitrogen from this. It only has manganese and nitrogen in it. So if I subtract out the weight of the manganese, this will give me the weight of my nitrogen. Again, guys, I now have the weights. First step gone. Second step, I'm going to turn them into moles. My 41.7 grams of nitrogen divided by my atomic weight of nitrogen gives me 2.98 moles of nitrogen. My 98.3 grams of manganese divided by my 54.94, this equals 1.80. No, and I'm going to have to call somebody that hasn't been here. I haven't. Miriam. You there, Miriam?
Yes. Yeah, I'm right here.
All right. Now, I took my grams, turned them into moles. What's my next step now?
You do the thing you're talking about, like the half divided by the whole.
I don't think you quite have it, Miriam. First step. First step, we found the grams. Second step, we found the moles. Now, I'm going to look at those moles. I'm going to find the smallest one. Miriam, which is the smallest one between 2.98 and 1.8?
1.8.
So I'm going to divide both of the moles by 1.8. That gives me a ratio of 1.65 to 1. All right.
Okay.
Is that a whole number?
Yes, it is.
1.65 is a whole
Oh,
number.
sorry. I was looking.
So what do I have to do now?
Multiply it.
All right. I'm going to start with times 2. I multiply this times 2. I get 3.3.
You gotta times it by 3 to get 4.95. Because that's close enough, right?
That's close enough. But if I multiply the 1.65 by 3, I have to multiply the other one by 3.
Hey, I have a silly question. I'm sure I missed it. So how do you know when it's close enough or just,
When you get to like a tenth within a whole number.
okay.
Okay, Monica, that should be pretty.
That
That should be
will
close
be
enough.
like, I'll be that person going crazy about that. So thank you.
Yeah. Yeah, I know it's kind of like one of those touchy-feely type things, Monica. I feel comfortable if it's within 0.1 to call it, okay?
Okay.
So now I got my molar ratio of 5 to 3. My nitrogen is going to be 5 and my manganese is going to be 3. So my overall empirical formula is Mn3N5. Questions, guys?
No.
I think, and if I'm not mistaken,
I have a question. So does the MN have to go before the N? So
Yes.
MN, okay,
yes.
why?
Cations always get listed before anions. Manganese is a metal.
Okay.
Okay, Katie? Always. Okay, I got to do one more thing and then my 2 more problems. A compound has an empirical formula of C2H4O. The molecular mass is 132. What is the molecular formula? All right, guys. Remember, when we went from molecular formula to empirical formula, didn't we divide by a whole number?
Yes.
So if I'm going from empirical to molecular, I'm going to have to multiply by a whole number, right?
Sounds right.
The way you get that whole number, if you take the molecular mass and divide it by the empirical formula mass, you will get the whole number. My molecular mass is 130. Okay, back off a second. Okay, I have a molecular weight of 78. We're going to back off this formula. We're going to do another problem, a simpler problem. My molecular weight is 78 and my empirical formula is CH. So my molecular formula is 78. My empirical formula is 13. If I divide 78 by 13, that number is going to be 6. All I have to do is take my 6 whole number and multiply it by the subscripts on each of my elements in my empirical formula.
Okay.
That will give me my molecular formula. Getting back to this problem, my empirical formula weight for this compound, C2, carbon weighs 12. 2 times 12 is 24. Hydrogen weighs 1. 4 times 1 is 4. 4 and 24 is 28. There is 1 oxygen. 28 and 16 is 44. That is my empirical formula weight. I divide 132, my molecular formula weight, by my 44, my empirical formula weight. I get a whole number of 3. So 132 divided by 44, that number is 3. I got to multiply each of my subscripts in my empirical formula by 3. That means the carbon subscript 2 gets multiplied by 3, my hydrogen 4 gets multiplied by 3, and my oxygen 1 gets multiplied by 3. So my my molecular formula is going to be C6H12O3. So when you are given a molecular weight and an empirical formula, to get the molecular formula, find the empirical formula weight, divide your molecular weight by the empirical formula weight, that will give you a whole number. You take that whole number and multiply it by the subscripts in the empirical formula, that gives you your molecular formula. Questions? Today's experiment. Basically, you're going to clean and dry a crucible. You're going to weigh that crucible. Then you're going to put about 5 inches worth of magnesium ribbon into the crucible. You're going to reweigh the crucible and the magnesium. Can you get the weight of the magnesium now?
Can we get a visual?
You have it right in front of you. You've weighed the dry crucible. You put the magnesium in the crucible and you reweighed it. Guys, how do you get the weight of the magnesium?
You minus what you got with what you started.
All right.
That's the best way I can describe it. Sorry.
No, that's fine. All right. So
you subtract the weight of the crucible from the total weight.
There you go.
Absolutely. Finest kind.
No, that's what I said earlier. Do I get extra credit?
You get as much extra credit as I'm going to give to Victoria. Every bit, not a bit more, not a bit less.
But you understood what I was saying, right?
That's why I went on, Victoria. Okay. Basically, what you're going to do is you're going to heat it gently at first. What happens is it kind of smokes. When it smokes, you put the lid back on. It cools down a little bit. You pull the lid off a little bit, then you really hit it with heat again. And you're going to hit it with heat for at least 10 minutes. At the end of the 10 minutes, all of the magnesium has been converted to magnesium oxide. So then you are going to weigh the crucible and the product. You have 3 weights. First weight is just the weight of the crucible. Second weight is the weight before heating, magnesium in crucible. So to get the weight of the magnesium, as Victoria and somebody else said, you subtract the weight of the crucible from the weight of the crucible and the magnesium. Next thing, you heat the snot out of this stuff. You make magnesium oxide. The crucible cools. You now weigh the crucible and the magnesium oxide. To get the weight of the magnesium oxide, subtract the weight of the crucible and magnesium oxide from the weight of the crucible.
Is it just from the crucible or the crucible and the magnesium strip?
Okay, let's look at this. Instead of magnesium, I did this experiment with aluminum. All right. I weighed my crucible to begin with. It weighed 15.435 grams. I put my aluminum in there and it weighed 943 grams. After heating, the crucible and the product weighed 16.394 grams. So my mass of aluminum is the mass of aluminum and crucible before heating minus the mass of the crucible. So I do that math out, I get 0.508 grams of aluminum. Now,
I have a question real quick.
just let me do this and I'll be right with you.
Okay.
The mass of the product is going to be the mass after heating minus the mass of the crucible. And that ends up being 0.959 grams. I'm sorry, Jeff, now your question.
So I thought that if we applied heat to it, oxygen would leave it.
Depends upon
so-
the circumstance. Depends
Okay.
upon, in this case, I have aluminum metal.
Yeah.
When I'm heating that up, there's oxygen in the air around it. So the oxygen in the air around it is going to react with the magnesium, and then it's going to make magnesium oxide. Okay, Jeff?
Okay. Gotcha.
The other thing we were doing was silver oxide. If I
Yes.
take the compound silver oxide and heat that up, I can drive all the oxygen away and be left with pure silver metal.
Okay.
You got that, Jeff?
Yeah.
All right, now I have the weight of my product, which is 0.959, and the weight of my aluminum. How do I get the weight of my oxygen?
Mass, it's on the screen.
Yeah, I
Mass
know,
product
Victoria.
minus the.
I like to give you these little hints.
You take the mass product and you minus by the aluminum that you got.
I could do it two ways. I could take the mass of the product in crucible and subtract the mass of the aluminum in crucible. That will give me 0.451 grams of oxygen. Or I could take the mass of the product, subtract the mass of the aluminum. That will also give me 0.451 grams of oxygen. Again, guys, the first thing we did, we found the grams of our elements. What's the next thing we have to do? We have the grams of the elements. What's the next process we use?
You gotta find the moles, right?
Got to find the moles. So I'm going to take my grams of aluminum, multiply it by 1 mole over the atomic weight. I'm going to take my grams of oxygen, multiply it by 1 mole over the atomic weight. Okay? Okay, so that gives me 0.0282 moles of oxygen, 0.0188 moles of aluminum. Somebody other than Victoria, answer this question. What do I do after I have the moles of the elements?
Divide both of those by the smallest mole.
And that is which number?
0.0188.
So I divide the 0.0282 by 0.0188. I get 1.5. The 0.018 by 0.018 gives me 1. I have a fraction. I have to use an integer. Multiply both by 2. I get a ratio of 3 oxygen to 2 aluminum. So I have Al2O3. Now, I also have the weights. If I have the weights, I can also get the percentages of aluminum and the mass percent of the oxygen. Remember, my whole weight is the weight of my product, 0.959. This is the weight of my aluminum. This is the weight of my oxygen. So to get my aluminum, I take my aluminum weight, divide it by the product weight. This gives me 53% aluminum. My oxygen weight divided by the product weight, this gives me 47% oxygen. Questions, guys? Any questions at all?
No, sir.
All right, quickly, I'm going to go through the results is a piece of cake, guys. Are you seeing the screen, guys?
Yes.
Yes.
First part of this is going to be almost exactly that aluminum oxide thing I just went through. Sorry, I'm gotta move you guys over. Okay. Simply speaking, you're going to, what you are given in the results, you're given 3 triple beam balance readings that you have to read. You're going to be given the first triple beam is going to be just a crucible. Second one is crucible and magnesium. Third one is going to be crucible and product. You got to show me how you got the mass of your magnesium. You got to show me how you got the mass of the oxygen. Then you're going to turn the mass of magnesium into moles, mass of oxygen into moles of oxygen. Any questions about this one? All right, you're going to have from the first part, you're going to have moles of magnesium and moles of oxygen. Next slide. Divide moles of magnesium by the smaller moles, moles of oxygen by the smaller moles. Show your work. I want the rough molar ratio here. I don't want the molar ratio after you've rounded or after you've multiplied by an integer. I want the rough molar ratio here. Then you have the rough molar ratio in this question. Next question is going to be the empirical formula. Guys, you know the answer to this already. Who can tell me what the empirical formula of magnesium oxide is?
Mg2O.
No.
Or is it just MgO2?
No.
It's just magnesium oxide, right? Because it has no
Well, tell me what it
subscripts.
is, Philip. Tell me
It's
what
just
the formula is.
Just MgO.
Just MgO, guys.
Just
Mg's a +2, oxygen's a -2. So you already know the answer you should have right now. But you still got to go through the math to come up with that. And by the way, that's the answer to this question. Okay, or no, that's the answer to the next question 6. All right, is magnesium a metal, guys?
Yes.
Yes.
Thank
yes.
you. So is this going to be ionic or covalent?
Ionic.
Thank you. Figure out which of the 2 ions. Got to click the correct 2 ions. He went to O6 minus?
Yeah.
Dear God, this is useless. Figure out what the charge on the magnesium and the charge on the oxygen is.
We just need the charges, right? We don't need like the subscripts or anything like that.
No, just the charges.
Okay.
Just make sure you know which one, that the oxygen is negative and the magnesium is positive.
Right.
Then what's the molar ratio of MgO? Now, you got another problem here with iron and oxygen. Solve this the same way we did the problem, both the aluminum oxide that I demonstrated and the one you're doing for this particular experiment. Same thing here. Okay, let's reason this out. What experimental errors might you have from this experiment? What could
I don't know.
happen?
We did our We do our math incorrectly?
Nah, I'm talking experimental errors. All right, let me give you one.
Don't use gloves.
No, I want to know what's going to affect the experiment so that it affects your results. One
So if
example.
she-
One example. You do not heat up the magnesium sufficiently and you do not convert all of the magnesium. Okay? How is that going to affect your results?
It's not going to give us the most accurate or true product that we
But
need.
Victoria, how does that
We're
affect your
half-assing it.
results? Is your molar ratio going to be high or low?
Low.
Low. It means we're basically half-assing our answer if we only heat it up halfway, if you think about it.
Okay, let me go through the reasoning with you. All right. You're not heating up the magnesium. Which weighs more, magnesium or magnesium oxide?
Magnesium oxide?
Because it's got the oxygen attached to the magnesium. All right. So if you don't heat up all the magnesium, do you get all the weight you should?
No.
So the weight of your product is low, correct?
Yes.
So if the weight of your product is low, how does that affect the weight of your oxygen?
Low.
Your weight of your oxygen is low. If the weight of your oxygen is low, then your magnesium is going to be your magnesium ratio of magnesium to oxygen. Since your oxygen is too low, the ratio of the magnesium to oxygen is going to give you higher molar ratio magnesium to oxygen than you should have. That's what you're meant to do in this question, guys. Figure out something that could cause your experiment to go wrong.
Are we allowed to put that answer? Or do you
No.
want us to come up with, okay.
All right. Let me give you this one. I'll give this one to you and you tell me how it affects the results.
Okay.
We're in Florida. It's very, very humid in Florida. So when this magnesium oxide was sitting around in the crucible, it sucked up some water vapor from the air. How did that affect your results? That's what I want you to answer for this question.
Oh, okay.
Do not tell me this answer. All right?
Okay.
All I want is for you to tell me water vapor is sucked up into the magnesium oxide that was created in this experiment. How does it affect the product weight? And subsequently, how does that affect your magnesium to oxygen ratio? That's what I want you to answer in this box. Fair enough, guys?
Yep.
And then do we need to find one more reason?
What's that?
And then do we need to find another reason?
No.
That's it? Okay.
Oh, I'll give you two things. You can answer the question as is, or you can answer that question that I just gave you. Either way, if you answer either one of them, then I will give you credit for the points, okay?
Okay.
Okay, thank you.
That's all I got for you guys.
Alrighty.
Monica.
Thanks, Professor.
All right,
No
thank you,
problem.
Professor.
Monica.
Thanks, Professor. See you next week.
Bye, guys.
Appreciate it,
Monica, bye. Stick around, Monica. Miriam, I'd also like you to stick around.
Are we all good on attendance?
Yes, you are.
All right. Thank you, Professor.
Bye.
I did actually have one question that I thought of.
What's that, Maverick?
How do we represent the Avogadro's number? Like like, do we type e to the 23rd power, or like how do we represent, something to the 10th power to the 10th? So do we just put e or something like that?
Just all you got to do is capital E, and then the number after the capital E is the number that would go as the exponent for the 10.
Okay, thank you, sir.
Good enough? Hunter,
enough.
you have a question?
No, I was just gonna say this is gonna be like downloaded or something. So because there's some good information in this one, I just wanted to listen to it again later.
Yeah, Hunter, Victoria is right. If you want that chart, it definitely is in the survivor guide. I also think it's in the lab manual. I'm not going to say for sure that it is. I'm like 90% sure it's in the lab manual as well.
All right, I appreciate it.
All right.
Have a great evening.
Monica, are you
Yes.
feeling a little good about this? Are you feeling okay with this?
Yeah, it's really good. So remember last week I was like dying with the moles, and then once I got it, I was like, oh, this is so silly. So yeah, it's good. No, this makes perfect sense. I'm gonna do my the week thing, the just not your lab, but like my regular class, and that'll kind of like solidify, and then I'll do my lab, and then it just works really good.
Monica, I would suggest doing this lab. Since you haven't had it in lecture yet, I would suggest you doing this fairly early in the week so that you have
Yes.
questions to ask me. I can get back to you, okay?
Okay, yes, thank you so much.
Good enough. All right. Take care, Monica.
Okay, thank you guys. Bye.
Miriam.
Yeah.
Okay, are we okay?
Yeah, I emailed you back. I said I apologize about
It's the only thing is sometimes when let me do one thing. I need to pause.
Okay.
Sorry, 1 second. I have to